So thank you for this introduction. As he said, I'm presenting our paper, Enhancing Lightweight Neural Networks for Small Object Detection in IoT Applications. And to introduce, I want to start with our motivation, which is that computer vision is becoming a powerful tool in IoT applications. And many of these applications require the detection of small objects. This illustration here shows a potential smart farming application where the drone is flying high above a field in order to really monitor, like for example, cattle. And to do this monitoring well, it must see all of the cattle at once and thus fly high above the air, high above the ground. And that means the objects will be quite small in the drone's field of view. Furthermore, we believe that this is a very promising area of research that can still be explored better. And to demonstrate that, I present here the performance data of some popular object detection networks on the Microsoft COCO dataset. And what we can see is that on the subset of the dataset that contains small objects, all of these detectors perform significantly worse. And that brings us to our research question, which is whether a lightweight small object detection system is possible that is suitable for tasks such as object counting and can run on low power embedded devices. And the second point is important because there's currently a trend in sensors that is moving towards onboard processing of the sensor data itself. An example would be an image sensor from Sony that has an image sensor together with compute power on the same board. And to capitalize on this trend, one has to overcome a few constraints. And the main one is actually low power that is available on these processing platforms that is in the range of tens to hundreds of milliwatts. And with this low power comes also very limited compute and memory capacities. So moving on to the state of the art, particularly in tiny object detection, or otherwise known as object detection that is capable of running on these constrained embedded devices, we identify FOMO, or faster objects, more objects, as basically the state of the art network for object detection in this use case. And it is able to do this because it solves a simplified problem, where instead of predicting bounding boxes for each object in the scene, it simply predicts the object's centroids. And this simplification of the problem allows it to use a very lightweight network, starting from the standard MobileNet v2 architecture, where they remove the deeper feature extraction as well as the classification layers and replace them with a very simple detection head, which, unlike a network such as YOLO, which for then each of the feature grid cells would predict multiple bounding boxes, simply classifies these grid cells as either containing an object or not. However, staying here quickly, while this network is actually capable of running on very constrained embedded devices due to this simplification, it's not very good at detecting small objects. This brings us to the key idea of our work, which is to tackle these drawbacks of FOMO and also the main challenge in small object detection in general, which is simply the lack of information for a given object, just due to their small size. And then in the context of embedded devices, this is made even worse due to their limited memory, which only allows us to process very small image sizes, further reducing the amount of information we have. FOMO itself is particularly sensitive to the size of the objects because of the way it makes predictions. In this example here, you can imagine a 64 by 64 pixel input image, which then results in an 8 by 8 feature grid on which the predictions are made. And in this example, the feature grid actually quite closely matches the size of the sheep in this example image, which in theory would allow it to predict the centroids of these objects correctly. But if we assume a smaller input resolution of the image, that also results in a smaller prediction grid, and then it can happen that multiple of the sheep actually land in the same grid cell, which prevents us from, for example, being able to count the objects correctly. A different problem actually arises when using larger input resolutions, because then it can happen that multiple of the grid cells are activated by the same object. And then we get a new challenge, which is to identify which objects belong to the same object versus which predictions belong to a different object. And it again becomes quite difficult to count the objects in the scene. And we will later see how using an F1 loss can help us tackle this problem. But first, how can we improve the general problem of this lack of information? As I stated earlier, increasing the image resolution is difficult due to the high increases in memory, especially in convolutional neural networks. So what we can do instead is use tiling to split images for individual processing. This allows us to use low image resolutions for the individual tiles so that we don't get increases in memory usage, while still getting the benefits of sort of enlarged objects within each individual tile, which you can see on the right side here. This does, however, come at an increased inference time since we now have to process multiple tiles for each image. Nonetheless, we do believe that this is the best approach to overcome these memory constraints. And so I'll show you how we implement this, which what we call an adaptive tiling, where for a given image, we first identify the average size of all of the objects in the scene. The average size we define as the size of the objects we define as the normalized bounding box area, meaning we get the area of a bounding box of one of the, in this case, cars in the scene, and then we normalize it by the size of the image itself. And so to get an average of all of this, we take an average of all of the bounding boxes of the individual cars, and we divide that by the size of the total image. In this example here, that would be about 0.2%, which is quite little. So you can imagine only 0.2% of the entire image is covered by a single object. So now what makes this adaptive is that we define a target object size. And this target object size allows us to control how large we want the objects to be in the later tiled images. And so for a target object size of 0.8%, that means we want to magnify the objects by a factor of 4. So the tile would have to be, in this case, exactly a quarter the size of the image. This allows us basically to not only finally control how large the objects are with respect to the FOMO grid, but it also prevents us from using more tiles than necessary. As you can imagine, a drone flying low will result in larger objects, thus we might not even need so much tiling versus a drone that is flying high. You may also have seen that this tiling can actually split the objects that we want to detect, and that means it could be harder to detect them. And so to avoid this problem, we slightly enlarge all of our tiles to get overlapping tiles, such that when some objects may be split on tile borders, they will always be fully in view of at least one of the tiles. So now I'll show you some of our experimental evaluation. We evaluate our method on the car part dataset, which, as the name suggests, is a dataset of parked cars. And first we compare to the standard FOMO network, the de facto state-of-the-art in embedded object detection. And here we're able to not only improve the F1 score by 63%, we're also able to reduce the object count error, which is the error of counting simply all of the objects in a scene, by 76%. Comparing to some more well-known object detection models like FASTER RCNN and YOLO, we're even able to outperform those. However, some newer methods like YOLO v4 can still outperform our method. However, here I would like to focus your attention on the last column, where we see the number of parameters that make up these neural networks. And you can see that for YOLO v4, this network uses 35 million parameters compared to the mere 19,000 parameters in our network. And this is exactly what allows our network to run on a device with little memory versus YOLO v4, which needs powerful hardware with powerful GPUs and lots of memory to effectively run. Now, I also mentioned this challenge where it can happen that multiple objects, an object is actually detected multiple times because multiple grid cells cover the same object. And here we see that training with F1 loss, as opposed to the classical binary cross-entropy, actually nudges the network into making only a single prediction for each object, which also drastically improves the object count error. Finally, I'd like to show you the benefits of this adaptive tiling method versus simply increasing the input resolution. We compare a network that we trained on a small 96 by 96 input size, and then compare increasing the image resolution with our tiling method that also runs on low input resolution images. And these metrics are computed by deploying our model to the Sony Spresense, a small microcontroller with about 1,500 kilobytes of RAM. And what we notice immediately is that using a higher input resolution gives significant improvements in the F1 score, so it helps detect the small objects, but it also comes at a large increase in the latency that it takes to run these calculations, and a very large increase in the peak memory that is consumed while inference is being run on the device. Conversely, using our tiling method, we get similar improvements in the F1 score, and we also make similar concessions in the latency, but we get basically the same peak memory consumption because we use the same image resolution. And this is exactly what makes this tiling method so powerful for memory-constrained systems. So to conclude, we were able to show that basically small object detection is possible on the edge, and that is possible because of our tiling. And we're able to outperform the state of the art in embedded object detection using this method. We also saw through our deployment measurements that this can really help in these low memory situations. And we saw the interesting fact of using F1 loss to train networks in reducing these double predictions for the same object. We're currently working on open sourcing this method, so in the near future it will be available to all. And we've also already started implementing these techniques in sensors like the Sony IMX500. With that, I thank you for your attention, and I'm open to